Hi everyone, in this video we're going to go through the theory for 3i and also 3j, because 3j is just an extension of 3i. So using matrices for transformations. So up until this point we've kind of just done transformations with mapping, or we can just read them if the function is written in the correct form. But we can also use matrices, and it's important that you understand how matrices operate because you will see them on the exam, or they have been on exams in the past. I don't know what this year's exam looks like, but exams look like, but you do need to be familiar with how matrices work. Now you'll notice what is common with all these matrices. All right, so just looking at the matrices for now, are these zeros along the diagonal. Right, and reflection in the line y equals x is a little bit different, so I'll talk about that one separately. Now the reason for those zeros is basically if we've got to the point xy or any coordinates, okay, so xy are usually a point that you're mapping. So we map it using a 2x2 matrix. So we've got a value here, which I'm just going to call A. And then we put a 0, 0, and then a B here. Now the reason for that is because when we multiply matrices, we go across and then down. So effectively, when we're multiplying, we multiply the row by the column. So our resulting matrix, or our product matrix, is going to be a 2x1 matrix, to think about that. So we've got, actually I might need to make that a little bit bigger. All right, so we have covered matrices before, so I'm not going to give you another lesson in matrices, but there is a video there if you need to go and have a look. But we don't need to know too much about matrices, but you do need to know how to multiply matrices. And these are quite simple ones to multiply. All right, so we multiply the A with the X, so we get AX, and then the 0 and the Y. So we've got plus 0Y. And then we move on to the next row and we multiply that by the same column. So 0 times x is 0x plus by. So you'll notice with our product matrix, we've got ax plus 0, so we're just left with ax, and 0x plus by is just by. Okay, so that's why we're multiplying by that 0, because we only want the x coordinate to be here and the y coordinate to be here. All right, if we'd had another number, say here instead of the 0, and I'll do that in, not pink, let's do that in blue. Oh no, what am I doing? Green. So if we had the number 2 there, then you would have 2y, and that would leave you with a plus 2y there. So you've actually got, you're considering the y coordinate as well as the x, which you don't want. Now, the only reason you would switch them, like we have here, and you'll notice that the 1, 1 is, takes the position, so they're kind of switched with the 0, is because when we have a reflection in the line y equals x, that is the inverse. So if we had to take the inverse, we just switch the x and the y around. All right, so just going through this. So this is extremely important to put into your bound reference if you are creating your own bound reference. If you're keeping this one, that's great. So reflection in the x-axis. Okay, so that means this value here is going to be negative. All right, and if you're doing it using function notation, it's negative fx. All right, reflection in the y-axis, this time the negative goes there. Dilation of factor A from the y-axis, so you can see we're multiplying the x-coordinate there by A, factor of B, so we're multiplying the B there. And then for an inverse, you're switching the positions, because when we're taking the inverse, remember we switch x and y. Now that's only for dilations and reflections. So this last row, we've got translations. Okay, so effectively we're adding in an extra 2x1 matrix. Okay, so when we're adding in a 2x1 matrix, we end up with x plus h and y plus k. And you can have h or k is 0. So you might only have a shift along the x-axis. So you'd have a value of h, and that would mean k is 0. All right. Now we don't actually, so we're not multiplying by hk. I should make note of that. We're adding it. So when we go through the examples, it'll probably make a little bit more sense. Okay, so using matrix methods, find the image of the point 1, negative 2 under each of the following transformations. So let's start off with question A. All right, so the point we're transforming is 1, negative 2. So it might be a good idea to also think about, well, what's the function notation? So we're going to be doing y equals 3 times f of x. All right, so let me just go back up here. So dilation of factor 3 from the x-axis. So, oops, where are we? So we're here. All right, so just getting familiar with the function notation as well as the matrix notation. Okay, so our matrix is going to look like this. So 1, 0. So the 1 here, because it's only a dilation from the x-axis, not from the y-axis. So we don't need to actually change our x coordinate, and 0, 3. And then we're going to multiply that by the point. So the point in the question is 1, negative 2. So we're going to multiply that by 1, negative 2. Now it's very easy to do this on your calculator, but it's also good to understand how we do that by hand. So remember, we go across when we multiply and then down. So your product matrix is going to be 1 times 1, which is 1, plus 0 times negative 2, which is 0. Remember, that's why the 0 is there. I don't really need to write that in, but I will for now. Then 0 times 1 is 0, and then 3 times negative 2 is negative 6. So that means, oops, put that negative in. So if we have the image of that point, okay, so remember it's x, y, so our point is going to be 1, negative 6. All right, next one. What have we got? Dilation of factor 2 from the y-axis. So this time we're going to have the 2 here, 0, 0, and then a 1. And we're going to multiply that by 1, negative 2. All right, and you can easily do this in your head, or you can do it on your calculator. So we're going to have 2 times 1 is 2, and 1 times negative 2. So your point is going to be 2, negative 2. All right, and then we've got a reflection in the x-axis. So we're going to have, I was going to do all the function notation as well. So that's y equals negative f of x. So reflection, we're going to have 1, 0, 0, negative 1 for a reflection in the x-axis. The point we've got is 1, negative 2. So again, multiplying it through, 1 times 1 is 1. And then negative 1 times negative 2 is 2. Now remember, when you're doing matrices that you use square brackets, coordinates you have curved brackets. So just be careful with that. Question D, we've got a reflection in the y-axis, so our function notation is y equals f of negative x. So this time we've got a negative 1 up the top there, and we're going to multiply that through by our point in the question, which is 1, negative 2. So negative 1 times 1 is negative 1, 1 times negative 2 is negative 2. So our point is negative 1, oops. Working so quickly, I'm ahead of myself. So negative 1, negative 2 is the image with a reflection in the y-axis. And last one, what have we got? A reflection in the line y equals x. So this time we've got a inverse. So you kind of know if we've got the point 1, negative 2, as in the question, then the inverse has to be negative 2, 1. So you don't really have to do matrices, and all of these you don't have to do matrices, but you need to understand how to read transformations from a matrix. Okay, so it's extremely important. But the matrix notation, we would then have a 0 here, 1 1, 0. Okay, so we're switching the x and the y. 1, -2. So that gives us -2, 1. Now on your calculator, to do matrices, we just go into keyboard and you can do a 2 by 2 matrix there. So 0, 1, we'll just do the last question. And then we're multiplying by, what was that, 1, -2. And then you can see your answer there, -2, 1. I didn't write it as a, probably should have written this as a matrix before I wrote the coordinates. Right, so -2, 1. There we go. All right. Let's move on to another example. Okay, so find the matrix that determines the composition of the following transformations in the given order and find the image of the point -3, 2 under this transformation. So we've got a reflection in the x-axis and a dilation of factor 2 from the x-axis. So this table here that I've done all this highlighting on, this is your reference. Okay, you always need to refer back to here to see where your numbers go. So we've got a reflection in the x-axis. So that means this, I'm going to put my zeros in first. So this value here is going to be a negative, but because we've got a dilation factor of 2 from the x-axis, it's actually going to be -2. And this is going to stay 1 because nothing's really happened to the x-coordinate, it's only the y-coordinate. So the image of -3, 2. All right, so 1 times -3 is -3. -2 times 2 is -4. So the point of the coordinates is -3, -4. Example 8, a transformation is defined by the matrix. Okay, so this is exactly the same transformations as before, all right, because we had the same matrix. So a reflection in the x-axis and a dilation of factor 2 from the x-axis. Find the equation of the image of the graph to the cubic equation, blah, blah, blah. All right, so here's our matrix there, and we're actually applying that transformation to xy. So 1 times x is x, -2 times y is -2y. All right, so they're our new points. So actually, sorry, I put my little dash on the wrong things. So the image of x and the image of y in a matrix is equal to x, -2y. So that means the image of x is equal to x, and then the image of y is equal to -2y. And this is similar to what we've done with the mapping. Remember, we get to this point. Okay, you can kind of think, well, how not complicated, but it's just longer to do matrices, but you need to understand how they work. So the x hasn't changed, but we do need to rearrange the y's. So we're going to have y equals y dash over -2. And then we substitute it into our equation. All right, so we've got y dash over -2. And then equals x. Now the x's hasn't changed, so just be careful because I've got the x dash. I don't want to be careless, and because we're cubing it, I don't want to read that then as x to the power of 13. Not that I probably would, because 13 is quite a high power, but I'm just going to do that just to be cautious. All right, so we're going to end up with y equals -2x cubed. Oops, actually, we're going to multiply this whole thing. So we're going to have x cubed plus 2x. All right, because when we're getting rid of this -2 on the bottom here, We're multiplying both sides by -2, so both terms on the right-hand side have to be multiplied by that -2. Then you can leave it like that. You do not need to expand it. And sometimes expanding, you're more prone to make errors, especially with negatives. But if I did, this one's not a hard one to expand, so we can do it anyway. So -2x cubed minus 4x. But you know, with that negative there, sometimes people make mistakes. All right, so you can see it's very similar to what we've been doing before. All right, with the mapping, we've just been writing it in matrix form. All right, question 13. I actually just did this one, but forgot all about this plus b when I was doing it. Oops. All right, so I've had to delete everything and start again, which is quite frustrating. All right, so in question 13, we've got a transformation is described by the equation ax plus b equals x dash. Okay, so you've got this type of notation, but they've told you what a and b are. All right, so it's just a matter of substituting that into this equation. So the value of a is 4, 0, 0, 2. Now this x is just the coordinates x, y. So we're basically multiplying those two matrices together, and then we're going to add b. Now that's what I forgot to do before. All right, so -1, 4 equals x dash. Oh, sometimes I do that when I do matrices. It's like whenever you have something on the top and the bottom, you put a vinculum in between. All right, so let's just expand this. When you're doing matrices, we do need to multiply this matrix first. So we're going to have 4x and then 2y. And we can also do this, add this matrix b. So we're going to have -1 plus 4. All right, so that's your left-hand side equals x dash y dash. All right, so the image of x is 4x minus 1. So we're going to end up with x equals x dash plus 1 over 4. And then the y dash equals 2y plus 4. So y is equal to y dash minus 4 over 2. All right, so it's very similar to what we're doing with mapping here. Sorry, in the second part, I just realized you can't see where I'm pointing, but we're using matrices. Now, you're not going to explicitly be told to use matrices, but you need to understand how transformations appear in matrix form. Okay, so let's substitute that into this equation. So our y is y dash minus 4 over 2. Actually, you know what, I'm going to get rid of those dashes just because we're cubing, it's just going to get mixed up. So -2, and then our x is x plus 1 over 4 plus 6x. So another x plus 1 over 4. All right, so let's tidy up the right-hand side first, and I've got to put a cubed in there, so we'll do that. Okay, so my numerator is going to be -2x plus 1 cubed, and then the 4 we can also cube, so that's 4 cubed is 64, plus, and then we're going to have 6x plus 1 over 4. All right, I'm going to multiply everything through by 2. So we're going to have -4. Now there's probably, as I'm writing this, a more efficient way of doing these fractions, but I'm going to keep going. All right, going into the next question. I'm going to take that 4 over as well. So I'm just going to tidy up this fraction. So -4 over 64, we're going to have on our numerator x plus -1 cubed, and then over 16, because 4 over 64 is 1/16. And then we've got plus 12 over 3, so plus 3, so 12 over 4 is 3. And then I'm going to expand that as well. So 3x plus 3, and then we're going to bring that 4 over as plus 4. All right, so just tidying it up one last time. Plus 3x plus 7. All right, so a lot going on there, but basically we've taken this curve, all right, y equals negative 2x cubed plus 6x, and we've applied two dilation factors. So dilation of 4 from the y-axis, I'll just explain where I'm, which is this number here, a dilation of 2 from the x-axis, and then we had a translation in the negative x direction of the y-axis by 1, and we've moved up 4. So to the left 1 and up 4. All right, so you can either do your mapping like that, just by reading the transformations, but you do need to be familiar with matrices as well. All right, I might end this video just with number 17 and do a separate one for 3J. So what we've got here is just mapping a transformation. So similar to what we've had before. Okay, so the new function, our transformation function. So you can see we've got dilation factors, or dilation of factor 2 from the y-axis, and then we've got move to the right 3 and up 4. So you can straight away just do your mapping the way you've been doing it, but you know, this is the matrix, so we're going to do it using matrices. All right, sorry, I just had a random number calling my phone, which is very annoying. And we've got x dash, y dash. All right, so x dash, let's do the matrix. Oh, why does my phone keep buzzing? My watch keeps buzzing. Okay, so x dash y dash as a matrix is equal to 2x plus 3. Notice that vinculum snuck in. There we go, need to get rid of that. And then we've got y plus 4. All right, so x dash equals 2x plus 3. So let's just rearrange that to get x on its own. And then the image of y is y plus 4. So y is equal to y dash minus 4. And we substitute them into our equation. So y dash minus 4 equals 3 x, which is x minus 3 on 2 minus 2 squared minus 4. Now, this is where sometimes if you're looking for shortcuts, these actually cancel each other out, which is awesome. And then we're left with y equals, all right, so we've got to do a little, what have we got in here? 3x over 2 minus 2. All right, so what we've got inside the bracket, I'm just going to put over 1, just do as one fraction. So I'm going to have a common denominator of 2. So that minus 2 is going to be minus 4 on 2. And then we're going to have x on our numerator, x minus 3 minus 4, all on 2 squared. So x minus 7 on our numerator, so squared, and then 2 squared on the bottom, so that's over 4. All right, so you can write it that way, or you can write 3/4 out the front, but basically that's our new image. All right, I'm going to leave the video there, and I'll do a separate one for 3J. Okay, bye.